In the earlier lecture, I was talking about the role of secondary refining in controlling the inclusions and entrapments. I talked about what are the desirable functions for the secondary refining stages, like deoxidation, which I have covered, then desulfurization I have covered, control of gaseous elements like nitrogen and hydrogen I have covered, then injection of calcium in the form of CASI, how does it help in inclusion modification, what are the limitations, what are the precautions one has to take, and then what is the importance of controlling the liquid steel temperature for getting the desirable quality. This I have talked about. I have not talked about, I think, decarburization as one important requirement for secondary refining. I had also talked about what are the different processes like ladle furnace, inert gas purging, vacuum degassing, how it helps in achieving the different issues or different requirements for quality enhancement. Then I talked about VAD, vacuum arc degassing, how does it help in the arcing, how does it help in increasing the temperature, controlling the temperature, and how is it helpful. I have talked about RH process, Russell-Heraus degasser, how does it help in controlling the gaseous elements like nitrogen and hydrogen. I have talked about IM, injection metallurgy, basically how CASI injection helps in modifying the inclusions, controlling the melting point of the inclusions and related issues. What I have not talked about till is the vacuum oxygen decarburizer, how does it help in controlling the carbon, which is very important. So, today I will be talking about that. Yeah, decarburization, it can be done both by vacuum as well as argon. If you look into the decarburization reaction, then it will be clear how vacuum or argon helps in decarburization. Basically, the decarburization reaction means carbon which is present as elemental carbon in liquid steel will react with oxygen, which when you inject oxygen it will finally go into the liquid steel as elemental oxygen, and this carbon and oxygen they will react, will create carbon monoxide gas. This is a gas, and then the equilibrium relation indicates that the Henryan activity of carbon in liquid steel multiplied by the Henryan activity of oxygen in liquid steel is equal to the the K, the constant, and the partial pressure of carbon monoxide. This is a gas. So, the activity of carbon monoxide is determined by the partial pressure of carbon monoxide. The activity of carbon is given by the Henryan activity of carbon. Since carbon is present in very small amount, oxygen is present in very small amount in liquid steel, the Henryan activity, which is equivalent to wet percentage of carbon, since it is very low amount. So, the Henry's law is valid, and so the Henryan activity in of carbon multiplied by the Henryan activity of oxygen is equal to the constant into the partial pressure of carbon monoxide. Now, this constant K, I have discussed about this earlier. For any reaction, it depends on the particular temperature, because this is a thermodynamic factor, it depends on the temperature. So, at a particular temperature this is fixed. So, therefore, if the partial pressure of carbon monoxide is it can be controlled, that means if it comes down, then this is a particular constant, that means it is fixed at a particular temperature. So, these two, the multiplication of Henryan activity of carbon and Henryan activity of oxygen, that means the wet percent of carbon in solution and the wet percent of oxygen in solution, multiplication of this factor also will come down, because this is constant at a particular temperature. If this comes down, this multiplication factor also will come down. So, in this process, for a particular level of oxygen, the carbon amount in solution will also come down. This is the technique, this is the principle of controlling carbon. That means, it is the technique by which decarburization can take place. for a particular amount of oxygen when it is put in liquid steel. So, how the carbon solubility can be brought down? It can be brought down at a particular temperature when K is constant by reducing the partial pressure of carbon monoxide. How is it possible? Let us now look into the possibility. It is possible by two ways. If you use vacuum, that means if you use a vacuum oxygen decarburization process, so the partial pressure of all the gases will come down. In the process, carbon monoxide also, partial pressure of carbon monoxide also will come down. Or if you use argon, that means if you are putting argon in the process, so which is called AOD, argon oxygen decarburization. That means along with oxygen, you are putting a lot of argon in the system, in the process, in the that helps in bringing down the partial pressure of carbon monoxide. So, either vacuum or argon, these are the technique. If you use vacuum, then the process is called vacuum oxygen decarburization. If you use argon, then we call it argon oxygen decarburization. Oxygen of course is necessary, because this oxygen will react with carbon and carbon monoxide will be generated. So, at a particular level of oxygen in the liquid steel, if the partial pressure of carbon monoxide is brought down, the amount of carbon can be in liquid steel can be lowered. That is the technique of decarburization. So, as I have mentioned, it is possible either using vacuum, that is in the process of VOD, vacuum oxygen decarburization, or using argon, which is called argon oxygen decarburization. So, either you use vacuum or you use argon in the process, you can bring down carbon solubility, carbon level in liquid steel. So, theoretically it can be calculated from this value of K and value of partial pressure of CO. So, theoretically it is possible to bring down from 0.05%, that means when you are starting the process, the carbon level is say 500 ppm, that means 0.05% carbon. So, carbon content in the liquid steel, if we start at 0.05% carbon, which is the normal level after BOF, basic oxygen furnace. So, if you use that liquid steel and if you want to bring down the carbon either by using vacuum or by argon, then it is possible to bring down to a level of 20 ppm either by using vacuum or by using argon. So, decarburization is very much possible, which is a requirement, maybe a requirement in secondary refining either by using vacuum or by using argon. In the process, carbon monoxide is getting generated, this is a gas, so it will come out of the system. So, no entrapment, there is no possibility of any entrapment, unlike deoxidation where alumina is generated, unlike desulfurization where calcium sulphide is generated or manganese sulphide is generated, which has to be taken out from the liquid steel to the slag phase, it has to be taken to the slag phase. Incidentally, here carbon monoxide is a gas, so the gas will bubble out, will come out of the liquid steel when there is a vacuum or when you are using argon. So, in the process decarburization will take place, carbon will come down from say about 500 ppm, that means 0.05%, to it can come down to as low as 20 ppm. So, this is the beauty of this VOD or AOD, it can bring down carbon level to a very low level depending on how much vacuum you are using or how much argon you are pushing, what is the partial pressure of CO. This will determine at a particular temperature how much of carbon finally will be there in the liquid steel. So, there is a good process, it is a useful process. Now, we have come to the end of secondary refining, that means we have tried to bring down the level of oxygen by deoxidation first. we have tried to bring down the level of sulfur by desulfurization. Phosphorus we have taken care of in the primary steel making itself, as I have discussed earlier. So, we have taken care of phosphorus in primary steel making, that means BOF or EAF. Then in the secondary refining, first step is to control the dissolved oxygen content, that means killing of steel, deoxidation of steel. So, that also we have I have told you how it is possible by using either silicon or silicomanganese, or the better is aluminum, which is a very good deoxidizer. And I have also mentioned to what extent deoxidation is possible. For aluminum, deoxidation is much better. It can be found out from thermodynamics that why aluminum is a very good deoxidizer compared to say silicon or manganese. So, after deoxidation we do desulfurization. I have also mentioned why deoxidation is first required. The dissolved oxygen has to be brought down, then only desulfurization is effective. So, these I have discussed. So, after desulfurization, what you do? You do degassing. You can take care of hydrogen and nitrogen, which are the gaseous elements, or even oxygen to some extent. It can be used like when you are using some carbon. So, it will react with oxygen. If you increase some amount of carbon in liquid steel, so some amount of dissolved oxygen also will come down. So, by degassing process we are controlling hydrogen, we are controlling nitrogen. I have also mentioned how vacuum helps in controlling this gaseous elements. Solubility of gaseous elements come down with the help of vacuum, and how it helps in reduction of nitrogen and hydrogen. I have also mentioned theoretically both hydrogen and nitrogen can be brought down to very low level, but in reality nitrogen reduction is a bit difficult because of kinetics, because nitrogen has to be removed. Nitrogen is relatively slowly removed because of the kinetic factor compared to hydrogen. Hydrogen diffusivity is very fast, so it can be removed relatively faster. So, the theoretical limits of hydrogen can be achieved, the thermodynamic limits of hydrogen can be achieved through degassing, but it is difficult to remove nitrogen to the theoretical level. So, what is necessary is removal of oxygen, removal of sulfur, because oxygen, sulfur particularly is a surface active element. If it is not removed before denitrogenation, then it competes with nitrogen for acting as the surface active elements, and it causes problem. So, desulfurization is a necessity, it is a prerequisite for removing nitrogen from liquid steel. So, I have talked about all these secondary refining processes, how these processes help in cleaning the steel, how these processes help in removing the undesirable elements to a controlled level, to a very desirable level. It cannot be totally removed, but you can control them, bring them down to the desirable levels, which is dictated, as I have told earlier, by the application requirements. So, depending on the application requirements, you can bring down dissolved oxygen, you can bring down dissolved sulfur, you can bring down dissolved hydrogen, dissolved nitrogen, you can bring down carbon if there is a necessity. All these are possible through secondary refining.